4.58. There were two concentric circles.
Here's, I got a radius. Tossing already. What's the outer one?
The outer one is B.
And then you got inner one A, right? Well, actually, this one's real small, right?
Yeah.
This is like this. Radius A.
And we were supposed to find the mutual inductance.
Right, now this is a typical kind of engineering problem where you have to use your head and get a basic understanding. You know, if you just have a current loop, all right, like this, I'll try to draw it like this. This is X, Y, and Z, and you have a loop in the XY plane as such. And say this is radius A. You know that in the z-axis, the H field in general is really going to be equal to 1 over 2, and then you're going to see, if that's rho, it's going to be, actually, let me do it this way, call this z and a. It's going to be a squared plus z squared to the 3/2 power, and then it's going to be times on top a squared, and there is no z on top here, and it's times I, and it's in the a feet, or in the a z direction. Do y'all remember that class when we did it? Right? Mm-hmm. And then if you look at this, that's the H field anywhere on the z axis. If you want it at the origin, H would be equal to simply, then z goes to 0, so you have a squared over a cubed, so it's simply 1 over a, 2a, 1 over 2a times I in the az direction, and this would be at z equals 0. Are you with me on that? So you're getting the H field at the origin from a current with radius A. So if this has radius A, and we assume a current, then we can say that the H field dead center here would be equal to simply AI over 2 in the AZ direction coming out of the board. Do you all agree with that? Now, if that's the H field, the B field would just be that times mu, right? Now here's the thing where engineers, good engineers see this. They know that the B field is not going to change much if we move radially outward a little bit. It's about the same because you're so far, you're basically, you've got a large loop and small movement at the center is not going to change the H field hardly at all. All right? And that's just something you're going to have to get used to in engineering. You can actually prove that if you wrote, this is only on the z-axis, but you could write the H field, the general formula for the H field anywhere at any point x, y, and z, and then take the derivative with respect to x and take a look at how it varies here, and then a derivative with respect to y and how it varies, and you'll see it varies a very, very small amount for small changes here, like a over 10. It doesn't vary much if you're talking about that kind of movement where, from the center point. So therefore, we say that the B is going to be about a constant in there, the B field. So that means the magnetic flux that penetrates this region created by the outer current would be simply equal to, there's only one turn, it would be B approximately equal to B times A, or it would be mu AI over 2 times pi B squared. You agree with me? It would be the area times the B field, right? Okay with that? You're suspicious. You don't believe me?
No.
What don't you see?
How did you get from H to B, first of all?
B is mu H, right?
Yeah.
Okay.
That's not mu H, is it?
Where?
I
That's
over
H.
2A.
That's H. Huh?
Your A moved to the numerator.
Oh, I'm sorry. My bad. Thank you. My bad.
And also, why? Wait, the outer loop is B, right?
No, inner. Oh, is that right?
Yeah, the outer loop's B.
My bad.
Okay.
So it should be 2B.
Here we go. This would be B. Right. This would be B. this would be B, and this would be A. My apologies. Agreed, class? And then for the inductance, the only thing you're going to say is the mutual inductance would be simply the magnetic flux through the second circuit divided by the current in the first circuit that caused it, or it would be mu times pi A squared over 2B. Does he have that as the answer?
That's what it was, yeah.
But that's how it works, and the real trick is to figure out one of these things that engineers have, they have insight and they can see that there's not much of a change in the B field, just call it constant there. All right. Anything else? Questions? That's a good question.
I was gonna say 4.54. Let me
Sure.
look up what it said.
One other thing too, on the schedule, we have one more test, and right now I'm looking at, next week is our last week of classes, isn't it?
We have 2 weeks.
Two more weeks. Sorry. We got next week and then the following week. And what I would like to know is when you would like your test. I'm asking you. I'll put it, if you want me to, I'll pick a date, but
24th,
when's that?
Wednesday, the 24th. And that would still give us time to study for the final, which would be the next week.
They're sort of, yeah. I'm gonna say this for the last time. Monday test usually the highest average, Friday's usually the lowest. Doesn't matter to me when you have it. Do you want a little more time to talk about it and we vote next time? Or do you want it, however you wanna do it, guys? Because I don't know if you know where your tests are in your other class. That's what, I would always schedule it on a day that you don't have another test.
When's our linear test? Yeah, so I have to look at my other classes.
Why don't you go ahead, I mean, if you wanna get at the end of class,
I want to say it's
what's that?
I think the other test you're talking about was on a Friday, so I think Wednesday would probably be okay.
This coming up Wednesday? Or
No, the last week of classes.
These are
last-
24th.
Yeah, it was just the last
Yeah.
week of classes.
Well, I'm curious, are you okay with this, everybody, if we do it on Wednesday, the last day of class?
Yeah.
All right, can you send me a note?
Yeah.
Just send me an email.
Okay.
All right, I wanted to make sure I got that out of the way. Now that I did, you had a question about,
Yeah, 4.54. Let me read it all.
okay, go ahead.
All right, it says, consider a long pair of straight parallel wires, each of radius A, with their centers separated by a distance D.
I think we did this one.
Yeah, it's just one of the answers that he got, I just didn't know how he got it.
Probably, and this is B?
Yeah, the center's distance D.
You want to see it?
Assuming D is greater than A, find the inductance per unit length for those wires.
Total inductance. All right, there's internal and external, right? So the internal inductance for a single wire, you just have a wire, L per meter is simply mu zero, or really mu over 8 pi, right? So if we do a per meter thing from here to here, then I can say I've got to take that one, so L total would be equal to 2 times mu 0 over 8, or mu over 8 pi, and this is going to be per meter. And I'm assuming current's flowing differentially, so I's flowing up there, down there. That's an assumption. And then after that, now we need the actual inductance associated with the flux length through that path right there, right? So if we're going to do that, then we're going to say that first, if you have a straight wire, the B field is equal to mu I over 2 pi rho A phi. And here I'm going to call this the z-axis, this is rho, and this is what my B field would be here. Now, if I use the same thing and call this distance rho here, that would be my B field here, correct? Now, what I want to do is get the total flux here. And last time when we talked about this, we could see that the flux from this current going up is into the board, and the flux from this current coming down is also into the board, so the flux add, right, from the two wires. The B field's in the same direction. And then I made the statement that if I integrate just the integral of B dot ds, where the B field would be from this wire, and integrate through this region, it would be the same as the amount of flux from this wire through here. Do you all remember that contention? Does everybody agree with that? All right, so therefore I say that the total flux through the region was equal to 2 times the integral, double integral of the B field, mu I over 2 pi rho, A d rho, in the A phi direction. And then I have to put limits on. Z, it's per meter, so I go from 0 to 1. And rho goes from A. Now, I'm assuming that's a radius, not a diameter, right?
Mm-hmm.
It's gonna go from A all the way out. And then if you look at this, since the centers are separated by that much, I have to take D minus A as my limit, don't I? Now, when you do that, that's the total flux, and I'm gonna just go right ahead and say, therefore, the inductance would be that divided by I. So if we just get rid of I, right here, this would be the inductance. This is going to be external inductance. So when I do A phi dot A phi, I get 1, right? And then when I integrate dz, it goes away because dz integrated is just z from 0 to 1 is just 1. And then when I integrate d rho, 1 over rho d rho, I get natural log. So this becomes mu over pi times the natural log of d minus a over a. And that should be his answer.
See, that's where I got confused, because his answer was mu over pi, and then in brackets 1/4 plus natural log of d minus a over
Well,
a.
does he give dimensions?
It just says L over H equals mu over 4 pi.
L. Oh, this isn't an infinitely long wire?
Mm.
You need to add the internal.
Yeah.
This is what it is for the external, right? This is what it is for the, this is the total, sorry, I didn't add this in. You have to, you're right, it would be plus mu over pi, natural log of, you can say it's d minus a over a, and that's the total. Now, how does he have it?
He factors out mu over pi.
What's that?
He factors out mu over pi.
Okay, well, then if he does that, that's fine. Mu over pi, and that's gonna be equal to simply 1/4 plus, and then it's gonna be the natural log of d minus a over a. That's what he has, it's
Okay, yeah, I got it now.
essentially. Any other questions about the homework? I wanna make one comment about magnetic circuits. I know they seem a little boring and they're more related to power and transformers, but they are important. Now, for magnetic circuits, I want you to think about one thing, how you would do a problem like this. This is me personally. I'm gonna ask you about this. Let's make a little gap here. So we're gonna have a current I here, have N turns. And let's say I wanted to analyze this with the analogies, and I'm gonna say that this cross-section here is A1, this cross-section is A2, that's A2, this is A2, that's A2. More or less, everything is A2 in cross-section except the middle one, it's A1, all right? Assume the whole thing has a permeability of mu, and assume the length, I'm going to do it this way. I'm going to assume the length, there is a colored marker, it'd be great. Let's say the length from here to here would be, call it L1, and from center to center here, call it H1. and assume it's symmetric, so from here to here, it would be simply L1 over 2, and from here to here, it would be L1 over 2 as well. Now, if you're looking at that, if I wanted to analyze this circuit, and assume that this is an air gap too, you had some problems with air gaps. Did you all remember those? In the homework I gave you, right?
Yeah.
Now, for this is a little more complicated problem, but not really. It's just a larger circuit. If I look at this, do you see that there's a reluctance here, effective reluctance, there's a reluctance here, there's a reluctance here, a reluctance here, reluctance of the gap, reluctance here, and a reluctance here, and then a reluctance in the center. Do you all see that? But what I can say is because there's no difference in cross-section all the way around here, I can go from this point to this point and say it's just one reluctance or one resistance. So I'm going to put it there. I can put a reluctance there. Matter of fact, I can make the voltage equivalent, the plus to minus N times I. That's a magnetomotive force, right? That's like the EMF, the voltage, right? This reluctance here, and I'll call it 1, that would be simply, think about this, from here to here is L over 2, right? L1 over 2. From here to here, it's L1 over 2. From here to here, it's going to be H1, right? So the length would be L1 plus H1, right? It would be divided by mu, and it would be divided by A2. That would be the reluctance associated with this length. With me? Now there's a reluctance from here to here. That reluctance, right, I'll call it R2, that would be equal to the length from here to here, or H1, always proportional to length, inversely proportional to A1 because that's the cross-section, and inversely proportional to mu. And I'm assuming mu for this whole thing is the same. It may be 1,000 mu naught, maybe 5,000, something like that. Understand? Now, from here to the gap, and let's assume that L gap is much, much less than H1, then we can say from here, right from this point to here, the total cross-section is the same in the material less the air gap. Forget the air gap for now. We're going to assume that the air gap is so small that it doesn't change the effective length. So that's L1 over 2 from here to here, right? L1 over 2, so it's really L1 plus H1. So here, you're going to see that this one, this reluctance from here to here is the same as from here to here, or it's really going to be R1. But then we have the gap, and the gap is going to have a reluctance. R of the gap is simply equal to L of the gap over mu, and then it's going to be A1. I mean A2. Now you all see this class, right? Please watch this. This is pertinent to the quiz, so that's the reason I'm going over it. Everybody see this? Now, if I wanted the flux, magnetic flux in the gap, if I wanted the magnetic flux there, that's like current, isn't it, class? That's like, so how would you get the current there if this was the electrical analog? Talk me through it. There's a couple of ways. Frankly, what could you do? Well, I mean, there's a couple of things you could do. You could just do a Norton equivalent, right? And put Ni and divide it by R1, get a current source, right? And then put R1 in parallel, then you have 3 parallel resistances, right? And then you would say, if you wanted the current through this leg of the resistance, you would take what? The other 2 you would have to get a lumped value for R1 in parallel with R2, wouldn't you? But you could do that by current division. Do you all understand that? You could also say, well, if I wanted the current here, what I could do is take this value, R1 plus R gap, as a single resistance, put it in parallel with R2, right? Get a parallel equivalent, put it in series with R1, and then simply take Ni divided by the total resistance, find the current flowing through here, and then do current division to find the amount through this other leg. But there are about a dozen different ways you could do it. You could write loop equations if you wanted, right? Or you could do nodal analysis. So what I'm trying to say to you is, this is a problem that has no one solution, one method to solve it to get the end result. You follow me? There are many paths to get the same answer. And that's one thing as engineers you have to understand. It's not just one way in a lot of circuits problems and a lot of engineering problems to get the right answer. By the same token, an inverse problem would be, suppose I gave you the flux in this leg, and I wanted to know what Ni product caused it, all right? Well, if I have the flux in this leg, automatically I have the voltage across here, don't I? Now, if I have the voltage across here, I have the voltage across here, right? And I can find the current flowing there by taking that voltage and dividing it by R1 plus R gap, agreed? Then I can take that current plus the current I gave you, or the flux, add them together and say that total current flows there, correct? Then I could say that that total current times R1 would be the voltage, right? Plus the voltage here, which would be R2 times the flux, initial flux I gave you, or current, right? And I could add that voltage and say it must be equal to Ni, right? So that's an inverse problem. Do y'all see what I'm doing here? And one thing about all the classes you take from here on, they're going to assume that you know circuits well, that you can do Thevenin, you can do Norton, you can do any type of analysis that deals with simple RLC circuits. They do this, and you have to understand this is one of the things electrical engineers do very well. And to be frank about electrical and computer, you have to know circuits very well. Not, I kind of get it. You got to really get it. It's not like chemistry where you can sneak into electrical engineering, kind of know chemistry, but you don't need to know everything about Arrhenius plots and activation energies of certain process. You can get away with it, not with this stuff. You got to know this stuff really well. So I'm making sure I said that today before I give you the quiz. Now, today, this is one of my favorite lectures, or we're into my favorite topics. Now we're going into the full set of Maxwell's equations today. Are there any other questions, by the way, before? Yes?
In the homework solutions, they solved the air gap one by assuming a B field.
Well, they state a B field, don't they? They give you a B.
I missed that in the problem then.
Well, which problem is it? Do you have it?
4.62. I mean, I did it this way. Like,
Well, wait. You don't just have a B field in the gap. Something causes that B field.
yeah, you get the Ni and the reluctances, but then just the solution. Would you want us to solve these this way?
Well, if
Would
I
you
ask for
find
flux,
B-
if I ask for Ni, you'd have to eventually get back to it that way. But if you wanted, out of curiosity, if I said this middle leg here had a flux of, say, 5 Webers, right? If I wanted the B field there, well, B field is what? That's Webers per meter square. So you take 5 Webers divided by A1. That would be the B field, right? And if I wanted H, well, B is mu H. You take the H field, right? And divide it by, if you wanted the H field, you take B divided by mu, right? But you can get any of these quantities based on what's given. If you want me to do that problem, I will. Which one is it now?
4.62.
Yeah, I got it.
Yeah, he's got it.
All right, we can do it. I don't think that was a hard problem at all, but I could be wrong. What does it have?
It's just a square iron core with air gap.
Is it circular or how's it?
Like, yeah, it's just a circle.
All right, they got a
And,
circle like this, right? And what?
An air gap on the right side and a Ni voltage source on the other side.
All right, hold on. So they got, I'll make the area gap in a second. You got something like this, and let's assume it's the constant cross section. And they have N turns, they have I going in, they got an air gap, right? And what did they give you? Go ahead.
The problem is the H field has a linear function of V.
Okay, so they got a nonlinear BH curve.
So that's what you have to get.
So is H down here and B here?
Yes, sir.
And what does it do?
It's a weird curve. Yeah. It's this one.
Oh,
That's what you have
all
to
right,
get.
let me tell you about these problems. These are typical things that you get in power and stuff. They're for transformers, BH curves. There's a linear region down here. You see how it's about a straight line? All right, down here, B can be equal to mu H, and mu is simply the slope of this line. This, whatever the height to width right here would be as a slope. And that's how you get mu, by estimating. Now, the way you gotta figure out is, are you working in the linear or nonlinear region, all right? So, here's how it goes. That's for the iron core here. They give you a radius, mean radius A, is that right? They have to give you something.
Yes, it's 60 centimeters.
So A is equal to 60 centimeters, and what's the cross-sectional area of this thing?
The diameter is 2 centimeters, so
This diameter?
yeah.
So it's 1 centimeter, so the area would be equal to pi times 10 to the minus 2 squared, right? All right, so that's the area, it's 60 centimeters. That means the total length here, I'm gonna ignore, how thick is the gap, or how thin, I should say? What's the gap?
1 millimeter.
Man, that's insignificant. So here's what we do. We're gonna take the total length of this core right here, call it L as 2 pi A, right? And then I can say that the reluctance of the core, right, is going to be equal to 2 pi A over, and then it's divided by mu, right? And times the cross-sectional area, which is pi, and that's 10 to the minus 2 squared. So that's the reluctance of the core. This is the tricky one here, the mu, but we'll get to that in 1 second. Remember, that's that weird function that we gotta estimate. Understand, class? So now you have this, that's the reluctance of the core. Reluctance of the gap is simply equal to the length of the gap, so it's 10 to the minus 3 over the cross-sectional area, which is pi times 10 to the minus 4th, and then it's times just mu 0. Now if you give me a value for this, it'll be helpful. Let's see, that's gonna be 10 over pi mu naught, whatever that comes down to. So mu naught is 4 pi times 10 to the minus 7th. So it would be 4 pi squared, 10 to the 8th. So 10 to the 8th over 4 pi squared, whatever that is. I'm not sure. Anyone? Does he give you N and I or not?
Yeah.
What does he have for N?
10 or 100.
N's 100? And what's I?
10.
10? 10 amps?
Yeah.
That's a lot. All right, so that means Ni is equal to 1,000 or 10 to the third, and that's amp turns. Let's see, so if we're building this circuit, we have 1,000 here. Then we have this gap reluctance down here, which is going to be whatever. Can you, anybody?
2.53 times 10 to the 6th.
And then what we have is this guy here. So that's going to be 2 times 0.6 over pi, or actually get rid of the pi, times 10 to the minus 4th. And then you have an unknown value of mu. So can you just tell me what 2 times 0.6, that's that's 1.2 over 10 to the minus 4th, so it's 1.2 times 10 to the 4th divided by mu is this reluctance. And here's why I need this. I need to get a first estimate of the flux, and that would be Ni, or 1,000, divided by the sum of these two. And we're going to start just using this one. Now, let me try to explain this, and I'm sorry I'm talking so fast, but just follow me on this. Here's what we have to do. We have to get an idea of whereabouts we are in terms of that nonlinear graph. We want to see where we are, all right? Here's how we do it. First, you ignore this reluctance completely of the core. And most of the time, the gap reluctance dominates, remember that. The core may be like 10 ohms, the gap may be 1,000. That's the kind of ratios you expect. Air gaps have a lot of reluctance. So if you take a look at this, the peak value, the max value of this flux here, I'll call it max, would be equal to 1,000, right? Divided by 2.53 times 10 to the 6th. Can you give me that? That's the flux. Just give that to me. You see what I'm doing here? It can't get any more than that. The gap wouldn't let it, right? This is the upper bound. This is where you start this problem. What do you get for that? The 1,000 is just Ni, and I'm dividing by the, quote, magnetic resistance, the reluctance, 2.53 times 10 to the 6th. Anybody?
3.95 times 10 to the negative 4.
Call it 6 times 10 to the minus 4?
Yes, sir.
Now, that's equal to the B field times the cross-sectional area, isn't it? Right? So that's equal to the B field times cross-sectional area. Therefore, the B field, matter of fact, let me do this. The B field would be this, 3.56 times 10 to the minus 4, divided by pi times 10 to the minus 4th, or by the cross-sectional area. That's the B field, but don't calculate that quite yet. I know the B field divided by mu would be the H field, right? Correct, class? But for now, let's calculate this B field. What do you get for this? The 10 to the minus 4th cancel, so I get 3.56 by pi. It's about what? 1.1, something like that, 1.2? 1.3? That's 1.3 Webers per meter squared. Now take a look at your funky graph. Who has the book open? Take a look at that graph. And look where you have 1.3 Webers per meter squared on the B field. Well, you can see right there that we're off scale, right?
Yeah,
So it looks like we're in a nonlinear region, correct, class? Right? If you look there. So here's what happens. Unless I read something wrong. I mean, do you all see what I've done here for the B field? That's the maximum, right? Now what you're doing is, if you're out here, he didn't show this well, but this is something to know about magnetic materials. In general, if you look at H versus B for all magnetic materials, it does this. It comes up, and this is related to just B here is mu H, and that's just plain mu H. But as soon as it hits this nonlinear hump and it comes like this, there might be some undulation. Out here, the slope goes to just mu naught times H is B. All right? There is no, it just goes to, mu relative becomes 1. It goes to mu naught, way out on this end, all right? So now what we do, it's an iterative calculation. We're going to assume that here, it's mu naught, all right? And we calculate this reluctance. And what do you see for that? By the way, I'm not sure that that's the right answer, that I had the right values there. This reluctance should be the length, which was 2 pi A. So this reluctance should be 2 pi A, or 2 pi times 0.6 over mu, which we're going to assume is mu naught, times the cross-sectional area, which is pi times A squared, or times 10 to the minus 4. And this should be this core reluctance for starters. And what do you get for this? Pi's cancel. So this looks like a fairly large value. Which value do you get? You see what I'm doing here? This is the length, right? This is the cross-sectional area. And we're using mu naught. We're assuming we're way in the nonlinear. What do you get?
got like 9.5 times 10 to the 9.
All right. Now this dominates this. All right. This is much, much greater than that. So now I'll take a look at this graph again. Actually, B divided by B here, I'm looking at this and it looks like at when I have 900 amp meters, this is a weird one, because that's not following the standard curves. 900 amp meters and B is 0.5. Tell me if I'm right about that. So H is equal to 900 amp per meter, and the B field is 0.5. Can you see that? Take a look where the H field's 900, if you can. And then you get a B of that, right? Now here's the weird part. Watch this value of mu. Therefore, what is mu? Well, mu times H is B, right? So B over H would be mu, and what happens? 0.5 over 900 is what? Well, that's really, take a look, what is that gonna be? Call it over 1,000, what do you get? That value is very large is what I'm getting. Our mu is what, 4 pi times 10 to the minus 6. What's this value gonna be?
5.6 times 10 to the minus 4.
What's mu naught? 4 pi times 10 to the minus 7th, right? What does that come out to be?
.25 times 10 to the minus 6.
You see how this is several orders of magnitude greater? So he's showing you a graph. I'm sorry, the way you really do magnetics problems is, you know, at the end, it always goes to mu naught. He's not even saying you're near the end here. He's not showing you. This is a weird material if it's a real material. So now what we have to do is assume that for starters as the value, this for starters, and estimate it. And that means instead of mu naught, now you've got what is that? You got 5.6 times 10 to the minus 4th here. And if I put that in, can you tell me what I get? If it's 2 pi times 0.6 over 5.6 times 10 to the minus 4th times pi times 10 to the minus 4th. I'm just replacing the value of mu. Anybody?
.14 to the 7 times 10 to the 7.
All right. Now I'm going to tell you how this is done. This is an iterative process. Now we use this, we're using the value of mu it's at the extreme side, right? Now you plug this in and add it to this, divide it into this, and you're going to get the flux. Take the flux, divide it by the cross-sectional area, you get the B field. Once you have the B field, right, then you take a look where it is on the chart. And you should iterate to a solution eventually. Now, that's the way you do these things, but it's a nonlinear problem, and that's the problem. He doesn't give you a mathematical equation for this for us to use. He just gives you a curve, but that's how, have you done nonlinear solutions before? Usually you start at the extreme. Get rid of the core material entirely, find out what the B field would be, right? If the B field is excessively large, then you start in at the extremes on the tape, on that graph. You start way over here. Use that value for mu. Then recalculate the value of B. Now, if B is now down here, then you use this value of mu, recalculate. And what you'll do is you'll start bouncing and bouncing, and finally you're going to land on the solution. It's a minimization problem. That's how he did it, didn't he? Duncan?
I think so. The solution was not super clear.
That's the way you do any nonlinear problem. You start by eliminating like the effects of the core in this case. Find the value of B. If it's in our case it's unreasonably high, it may be very low also. All right, it may be product B field in the linear range. Then you grab that value of mu, use it, and it's going to change it a little bit, the value of B, and then you refine the mu and calculate, again, the reluctance and how it goes, okay? But that's how you do those problems. And they're a pain, by the way. Most of the time, by the way, this is for your benefit. When I have to do anything nonlinear, and I have a graph, I take that graph and I'll take maybe 100 points and I identify them. And MATLAB has a tool, well, it will find an approximation, a mathematical function that gives a close approximation, and then I'll just use that function and write the formal equations and solve it. But I've had to do that many, many times in my life.
Oh, is it 'cause the H is, or H equals 200? Oh, might be 'cause the temperature's roughly.
Does he start by guessing that the core has no effect? Can you tell me?
He guesses a B field and then uses that to find mu. He uses that to find a
Well, you
reluctance.
can't just guess a B field.
Well, that's what he does in the solution.
Yeah, he
Yeah.
assumed B equals 0.4.
That means what he did is probably took Ni, Ni divided by the reluctance of the gap, right?
You know,
Is this what the B field is? If you take Ni, that's 1,000, right? What's the reluctance of the gap again?
2.53 times 10 to the 6th.
And then if you get that, you can get the H field in the gap by dividing it by the cross-sectional area, right? And then divide it by mu naught. Now that H field is the same throughout the core. All right, the B field will change, but the H field won't. Do you follow me? H field is like the E field. So-
Technology.
So what does he get for the H field?
Oh, so he read from the chart and he said that H equals 200.
Yeah, but that's not the way he did it.
Here's
what he
H
did.
equals B over mu naught.
No, he started by this. He took Ni, he ignores the core, then he divides by the reluctance of the gap. The gap is simply length of the gap, right, over mu naught area of the gap, area of the gap. Now, that's going to be the actual magnetic flux flowing, right? This is like voltage over resistance. Then you take that and divide it by the actual area of the gap. You'll notice they cancel, right? Now that's the B field, right? Then I divide it by mu naught, and I get the H field, right? You'll notice this cancels, and I have Ni divided by the length of the gap. What do you get for that? I'm just going to show you this.
Just 10 to the 6.
Yeah, if it's one millimeter, that's right, 10 to the 6, all right? Now, if that's the H field, 10 to the 6, is that even on the chart there, 10 to the 6?
No.
All right, that means that it's obvious that the core is gonna limit this down. Or else he would give us a value. So now, the next thing is, you're gonna start at the high end. Where was his guess for the B field, or for the H field?
200 for the H field, 0.4.
Well, then he knew the solution. He should start out here at the extreme. He should have started at right here where it's 1,000, take the mu there first, but it would iterate down to that solution. Something was funny about that problem. I got a feeling it won't work. There might be something I'm not saying, or maybe he just didn't feel like doing an iteration. It's a long process, and he guessed carefully because he knew the answer beforehand, but I'm really not sure. All right, you're not going to get a problem like that. Any other questions? All right, today what I wanted to cover is going to be Maxwell's equations. And if I don't have time for the quiz, we'll take it on Monday, but I want to just say this. I mean, I'll try to give it to you today, but I want to make sure I cover this. This is essential, it's important. These are the complete set of Maxwell's equations, so write these down. These are based on experimental measurement, and they are as good as it gets. There's no, even with relativity and all that stuff, these still work, even with general relativity. So the first is curl of H is equal to J plus the partial of D with respect to T. Before it was curl H just equaled J. Now the partial of D with respect to T comes in, and I'll talk about that in a second. And the second is curl of E is equal to minus dV dt. This is called Ampere's law. Ampere's law. And this is called Faraday's law. Faraday's law of induction, to be more. Now, thing that couples all these things or relates all these terms together are that J is equal to sigma times E, that D is equal to epsilon E, and that B is equal to mu times H. Those are the couplers. I call them couplers. They relate all the different quantities to each other. And you could see that if you wanted to, you could relate D to J, right? Because E is J over sigma, so you could put EJ over sigma is D. And you can see how they all relate, right? D and E and J have a direct relationship, and B and H have a direct relationship, okay? Now, with this, we're gonna start here, and I'm gonna show you how various things that happen in the atmosphere and other places can be figured out or gotten by just solving these equations in different ways. First thing we're gonna do is take a divergence of the curl of H. By definition, the divergence of a curl of any function is zero. It is defined as zero. It is always zero. So that's equal to the divergence of J plus the divergence of the partial of D with respect to T. Remember, it's zero, right? Now keep watching this. This is called the continuity equation, comes out of this. It's very important. So the next thing is that means the divergence of J plus, now I can take this divergence operator inside the time derivative because time and space are mutually, they're separable terms. One is not dependent on the other. Is equal to that plus the partial of D, or partial with respect to T of divergence of D, and that equals zero. All right? Now, do you remember what divergence of D equals? Anyone? It's the point form of Gauss's law. It equals what? Rho V, right? It's the volume charge density. Do you all remember that? Remember, the integral of rho V over the volume is equal to the charge enclosed. And it's also equal to the integral of d dot ds. That's the integral form of Gauss's law. The point form is divergence of D is equal to rho V. So now I can say that divergence of J plus the partial with respect to T of rho V equals zero. And this is the continuity equation. And that's an important one, but we're going to keep working on it. Div J plus d rho dt equals zero. This has an analog to something called Kirchhoff's law. Remember with Kirchhoff's law, all the current into a junction had to come out of the junction, right? Or accumulate charge there, right? Remember that? What goes into comes out of or accumulates. And this is the differential or the volumetric form of Kirchhoff's law right here. Now, something else. Since J is sigma E, right, I'm going to do it here. J is equal to sigma E, right? And E, right there, is equal to D over epsilon. Right? I can go ahead and plug in for J there, and I have the divergence of sigma over epsilon times D plus d dt of rho V equals zero. And if, write this down, make sure you put this, if and only if sigma and epsilon are constants, then I can take them out in front here and I have sigma over epsilon times divergence of D plus d rho dt, rho V dt equals zero. You want to take a guess at my next step? Anyone?
Swap in rho V for D again.
Div of D is just rho V, that's exactly right. So then you come down to this equation. You have rho V times sigma over epsilon plus d rho V dt equals zero. And that is a decay equation, or this is going to define exponential decay And here's what I mean by this. The solution to this one is just rho v of t is equal to some rho v naught, some initial value, times e to the minus t over tau. And tau here is simply epsilon over sigma. And this is called, by the way, this is like R. Remember when you had a time constant, RC was a time constant? Do y'all remember? This is the same thing. This tau right here, tau is the time constant. And it's really the time it takes for the charge to decay to 1. It took about 37% of its peak value. So most of the charge, about 66% of the charge is already decayed by the time one time constant passes. By the way, this brings me to my next point right here. If you thought about how long it takes a charge to decay in the atmosphere, you would probably be scratching your head a little. I'm trying to think of what you could actually think about that involves charge decay. Has anybody ever taken a balloon, rub it on your head, and stick it on a wall? How many have? You've seen it, right? You know. All right, well, it sticks there for a while, right? But what happens? At about 3 or 4 minutes later, it starts falling down, doesn't it? If you've ever done this, it's usually one of these things you don't forget. Well, that's because the charge started leaking off. It came from your hair, and it came leaking off. For the atmosphere that we're in here, the value of sigma is about of the order of 10 to the minus 14th, 1 over ohm meters. That means the time constant, epsilon over sigma being the time constant, would be epsilon naught, which is really 8.854 times 10 to the minus 12 over 10 to the minus 14th. And I'm going to brute force this. I'm going to just call this 10 to the minus 11th. So 10 to the minus 11th over 10 to the minus, this is 10 to the minus 14th. So if you look at this, right, you get a value of 10 to the third, or about 1,000 seconds, right? 1,000 seconds, and to be frank about it, if you think about that, 1,000 seconds, if you divide that by 60, is 100 by 6.
16.7.
So about 15 minutes, right? And that's usually about the time it takes to get 2/3 of the charge gone, right? About 15 minutes. But for these balloon things, I remember we were screwing around with this before. You don't need to lose that much charge before it starts falling, because the balloon has a weight to it, mg, and it's basically sticking on the wall barely, usually when you do these things, if you do them right, or sticking it to something. It's almost ready to fall. You only need to lose about 10% of the charge before it starts to fall. So that's just one of these things that makes it a little more real. That's the first thing. This is called the continuity equation. Would anybody mind if I gave you your quiz Monday?
I have a test Monday.
Oh, you do? Does anybody else have a test Monday? Do you have a class? You have a class right after this, right? All right, tell you what, I'll make a deal with you. I will give you, this is a homework problem that you're gonna hand in to me on Monday, all right, instead of a quiz. But would you do me one favor and not work together? That's the only thing I ask. I can't prove it. I'm just asking you to do this. Oh, heck, I really am trying to get grades that are reflective of your abilities. Could you just pass this thing out? This is a good one too. But I think everybody can do this. Just bring it in as a homework on Monday, and I want to continue with this lecture, okay? Because this is important. And that means you obviously can use your books. All right. Now, the next thing I'm going to talk about is, and I'll give you homework problems about this that's related to just the continuity equation. So the continuity equation was divergence of J plus d rho V dt equals 0. And again, typically you can also say that, that when you have rho V over tau plus d rho V dt equals 0, that's another form of it. But these are the two forms we use all the time to solve problems of charge decay. Next, we talk about Faraday's law of induction. So please follow me on this. When we have the curl of H is equal to minus the partial of B with respect to T, this is a powerful law. Now, I mean curl of E, pardon, curl of E. Curl of E is equal to minus dB dt. That's Michael Faraday's law of induction, or really, it's called the law of induction, but I gotta explain something to you. Curls generally don't make a lot of sense to you. You don't know what they're talking about. Curl really is the definition of the curl of E. You don't need to write this, just listen. Is the limit as really as delta S goes to 0 of the integral of E dot dl around a closed loop counterclockwise over delta S. Now that still doesn't tell you a lot. But what it amounts to is if you think about E dot dl and integrating around a closed circle, really it's almost like a voltage, but you know it's not electrostatic voltage. This has to do with the time-varying magnetic field inducing a voltage, transformer action. So if you think about a total voltage around a length of wire, whatever that is, and you divide it by the area, it's kind of a weird unit system. It's voltage divided by area, right? But in the limit it is, it shrinks down, it gives you an idea of what's, some people call it a vortice. If, you know, when you talk about tornadic activity, how can a tornado occur? Well, what do you really have? It's circulation around a center, right? And what's causing that circulation? It's a low pressure in the center, high pressure on the outside. And the reason the particles can't just rush straight to the center is that they already have some initial velocity, so they move in a circular orbit, and they kind of, as it gets closer and closer to the center, it spirals faster and faster. That's tornadic activity. But the way they gauge that is with the rate of circulation, and that is a curl type operator. So try to understand, curl has to do with like the intensity of circulation. It's sort of the only way I can think of that, trying to explain this. But we can do this, and we can take this and invert it into a macroscopic domain so we can actually see what goes on. That's what I'm about to do. If I integrate both sides of these, right? Now let me do it over here. If I integrate the curl of E, right, dot ds over a closed surface, so now I'm going to say I have some surface S, and I'm going to go ahead and take the curl of E and multiply it by the differential surface S. That's also equal to minus d dt of the integral of B dot ds. Now this is getting a little more familiar. Now I know that B dot ds is really the magnetic flux. So if I have a loop, let me do it here so you can see it better. Write this down. Let me call this point A and B, and I'll say that, make this better yet. Make it plus, minus, and call this V, EMF. Do this. Put that down. The loop has an area A. Right. Now, if I think about a B field coming out here, say it's constant through there. When I think about the integral of B dot ds, what do you think about? What's the term for that? Integral of B dot ds? It is the magnetic flux, right? Sure. So this, you can think about as just minus ddt of the magnetic flux penetrating some surface. And the surface here I have A, you could say it's vector S. So that's the flux that's penetrating surface S. Now, if you integrate E dot ds over that same surface, that becomes, this is the E for on the perimeter, identical to saying it's the integral of E dot dl around in a counterclockwise direction around this. This is why I'm trying to bring out the curl into the open arena so you can understand a little better. If you go ahead and integrate it, if this wasn't broken here, integrated E dot dl around that closed loop, you would get a voltage. And that voltage would be VEMF. And you'll notice it's a counterclockwise integral. So it's important to understand that. That means when you integrate B dot ds, the B field through this loop, and you probably should have some coordinate systems that would be x, y, and z. So I'm assuming the B field's in a positive x direction. Integral of B dot ds, then taking a time derivative of it, then throwing a negative sign in. That's going to be equal to the voltage induced on that loop, but such that this would be the positive and this would be the minus terminal. Do you all see that? Now what I'm going to do is a problem to try to expose how this works. And this is real important. This is the basis of transformer action. One thing I'll say too about this, listen to me. The B field would be caused by currents. The only way over here we get a non-zero voltage is if the flux is time varying. You see that? If the flux is a constant, there is no voltage. Understand that, class? So the flux has to be time varying. So here's a problem, and it's a good one. I'm going to go back to one I always use. I'm going to say I have a current of wire, an infinite current of wire, and I is equal to, say, 10 times the sine of 20 pi t, and that's the current in this direction, and it's on the z-axis. And then I have a loop, like so. I'm going to have a loop, a little gap here, and I want the voltage plus the minus there. That's what I'm looking for. And just say this is dimension A, this has width and height. All right, so I want to figure out what that voltage is, V right there, as a function of time, where the top part is positive, all right? This is a good problem to expose how that phenomena we just talked about, dictated by Michael Faraday's law of induction, can be used to calculate this. By the way, I'll tell you this, if I have time today, about something you can do with lightning, how you can actually see sparks fly through wires, if there's nearby light. Anyway, take a look at this. So how would you do it? Well, I'm looking for the integral of B dot ds fundamentally, am I not? So first I got to say what the B field is. So I'm going to introduce a coordinate system. I said that was z. I'm going to say this is x, and I'm going to call that y. Doesn't matter though. Agreed? What's the B field then from this? Anywhere. In this plane, is it into the board or out of the board? It's pointing in, right? And as a matter of fact, the B field, if this distance is y, that B field would be equal to mu 0, assume it's in the air, I of t, remember it's a function of time now, I'm just going to leave it as I of t, over 2 pi y, right? And it would be in the minus ax direction. Do you agree with me? Class? Right? All right, now I need the total flux through this loop. I need to find out the entire magnetic flux. So the magnetic flux would be what? The integral, double integral, of B mu naught I of t over 2 pi y minus ax dot ds. What would ds be, people?
D road.
Well, dy in this case. dz in the a x direction, right? It's got, and by the way, this is the standard way you get ds if you want it. But if you're looking at the problem, take your right hand, just wrap it around the differential surface. Your thumb points in the direction of the surface vector, which is out of the board, which is positive ax. All right. What are the limits? Y goes from where to where, class?
0 to h. Oh wait, 8.
A to A plus W, right? And where does Z go from?
0 to 8.
0 to H, right? You had the, you were giving me Z first. Y'all see this? AX dot AX is gonna be 1, right? So don't worry about that. So that means my flux here, magnetic flux, is minus, and then it's gonna be mu naught I of T over 2 pi. It's times H, the height, because dz integrated to Z from 0 to H is just H. Then when I integrate 1 over Y, I get natural log of A plus W over A. And you're gonna see this, those natural log integrals, I mean, the 1 over rho integrals happen all the time in engineering. Now I've got that as my flux, right? And I forgot one thing, no, I've got the minus sign. Now I need to take the time derivative of it, right? Can you all see with this, that the only thing that varies in time is I, right? So what I can really say is minus d phi dt, magnetic flux with respect to time, is going to be equal to minus mu 0 over 2 pi times h times the natural log of a plus w over a. I'm going to break that out as a single term, and then it's times the time derivative of I. Well, if I is that, the time derivative of it would be what? Can you see it? It would be 20 pi, right, coming out in front, right, times 10. Then it would be times cosine of 20 pi t, right? You agree with me? All right, now we have the flux, and I want to tell you one other thing. Normally, this term that I bracketed is called the mutual inductance. We calculated that before. So the mutual inductance times the time rate of change of the current in the primary circuit gives you minus d phi dt, which is equal to what? That's equal to the voltage, right? Now listen to me carefully here. That's the voltage, V, and it's really V EMF of T. And here's the important part. I got this voltage, wait a second, sorry. This is the flux, right? Now when I put the minus, see, this is the flux itself and it's got a minus sign, right? Now when I take the time derivative, that's what I get without the minus sign. Follow me? This is just the time, this is the time derivative of that. But the formula says I have to take minus d phi dt, so it makes this positive. And that is VEMF of T. But this is the part you have to appreciate. Do you see the steps I took to get this, everybody? Right? I found the B field from the current. I integrated the B field over the cross section, or really over the surface. Then I took a time derivative of that. After I did that, I multiplied by a negative sign, and I set it equal to VEMF. And that means the voltage found by integrating E dot dl around here, such that this will be positive and this will be minus, will be in fact this right here. And what it is the mutual inductance, this is the mutual inductance, times the time rate of change of the current. It's the di dt of the current in the primary. And really this VEMF, and this is a nice thing to know, of T, is equal to the mutual inductance times di dt in the primary. Okay? Something to keep in mind. I've got about 2 minutes. So that's basically showing you how to calculate the voltage in a single contained wire. I'm going to go through transformer action next time. I don't have enough time today, but I got to tell you a story. You know what? Y'all know what lightning is, right? Cloud to ground lightning is that spectacular event that gets about 20 to 50 kiloamps peak current, and it's very bright, heats the atmosphere up. You hear loud thunder caused by that. Well, there's a fair amount of current there, and it's very long. So the B field from that, lightning doesn't always hit straight down, it comes at angles, but the B field from that would be mainly in the horizontal plane, right? Unless you get odd arcing of lightning, like sideways lightning and stuff, or intercloud lightning, which is usually horizontal. That's between cloud to cloud. So what we didn't, what people do, let me rephrase that. Where's that? This is a parable. So I'm not gonna be legally responsible for anything you guys do in case you get injured. But if you live in an apartment complex in Huntsville, off Gate 9, called, well, never mind what it's called. And you happen to have a bunch of shellac copper wire, and you walked around that, about a little over a quarter mile. Walk around and make 5 or 6 loops, and then break the 2 ends of copper so they're no more than an inch apart, and watch a lightning storm come in. And lightning creates a big B field, and it theoretically would induce a large flux change through those wires, and there's N turns there, right? And you just might see a spark. Every time there's lightning, you would see a spark. Now what's interesting, that's one way of detecting lightning. If you had this inside a building, you could do this, and you would know there'd be lightning outside, assuming it's not solid metal, because that would shield it. But if it was got a porous concrete or something. Now another thing, do you know who Benjamin Franklin is? Right, he's on the dollar, the $100 bill, right? Yeah, Ben is a famous man. Well, Ben was also the first real atmospheric scientist, the first lightning guy. And the way he found a method to detect lightning, and don't do this. But what he did was he took a rod, a steel rod, and he put it through the roof of his place of residence, and he put it way up. And then at the base of that steel rod, or copper rod, he took some thin conducting twine, and he had 2 pith balls on it. You know what a pith ball is? A real light thing that can hold charge, sort of like that balloon. And he put it there. Now every time lightning or a thunderstorm was in the area, what happens is you have a large negative charge inducing a large positive charge on the earth. Well, when charge is induced, that pole felt the induced surface charge, and the charge, you might say a voltage, and the pith balls would start moving apart. Now he noticed that. So then he thought, what if I put something, a slight amount of metal at the ends of those, make it a little heavier, and then I put a bell around it. This is called Franklin bells, you can look it up. And he found out, and the bell is going to be tied to ground, by the way, so the outer part of the bell, but the inner part just to the rod, so it's isolated. So anytime lightning had happened, what happened is these pith balls would charge up fast and bang into the bell, and gong, and then they discharge, so they go back together, then charge up, bang. And the more rapidly the ringing was, the closer he knew the storm was, and the more likely lightning was going to strike nearby. And sure enough, it hit this place more than a few times, which is another story. But the story that you hear about, do you remember the story? What do you hear about Ben Franklin? There's one story everybody hears. A kite with what? A key, right? A key at the end is, and that is complete fallacy. He never did that, but I mean, it's all over the place. As far as I know, it's false. Because, you know, see, if a kite gets hit by lightning, guess what happens to the guy holding straight? He gets hit by lightning, and he will not survive that. That did not happen, but everybody hears about it. Franklin bells are real. You should look them up. That's 2 ways of finding out that there's a storm in the area.